we can start. Yeah.
Cool.
So yeah, I guess let's just discuss a bit about conformal field theories, two-point functions to be specific, and some interesting relations that we could derive from, analyzing this two-point function. And yeah, let's see how it goes.
Cool. So I have Blackboard duty, and the name of the game will be to leverage symmetry.
Yeah.
So conformal field theories are actually a subset of more general quantum field theories that enjoy Poincare invariance. Right. So you can define these in how many dimensions you like. And it's basically the group of translations. So we'll stay in Euclidean signature.
Rotation.
Semi-direct product with
yeah
rotations. Okay, hope I got that right. And what we're asking about is a two-point function between two operators. Well, actually, let's start with a one-point function. So what do I need? X. Right, and I'm on RD. So in quantum field theory, like we could ask, what could this be? And as such, you can't say all that much. Just say, well, it's some function of X. It's your job to compute it. Well, but then you could say, I talk about a point here. How does it transform under translations and so on? And can I talk about rotational invariance and whatever? But you can't really do that much. In examples, you find this to either be a constant that you could set it to 0, or sometimes it's non-constant. And famous example is the vacuum expectation value of the Higgs field.
Right.
So if I take the Higgs field in the standard model, then in the spontaneously broken vacuum like ours, there's going to be some non-trivial function here.
Right.
And in this case, actually, this is a bit more than symmetry. You tend to find that this would satisfy the equations of motion. So whatever the equation of motion is in the classical theory, so I'm writing it in this abstract notation because it could be a composite operator. Right, so the Higgs field here would just satisfy its equation of motion straight out of the Lagrangian, but you might have to work if it's something more complicated.
Okay.
And this is a consequence of something known as the Schrödinger-Dyson equations.
Right.
Okay, and that's all great, but you need to know what the theory is, as in you need to know what the action is and so on if you want to be able to determine this equation, or if you want to be able to determine this function in turn. Right? Because I can go back from here to here.
Right.
So that would be the way to determine. So, okay, we're comfortable with having a function as an answer now.
Yeah.
So now we can ask about the two-point function. So let me not write commas. So what do you guys think this could be?
So this would be 1 over some x minus x bar 2 delta or something like that, where
Well, we're still in quantum field theory though. It could be, but it doesn't have to be.
Oh.
So generally, what could it be? Like I just have one grain variance. What can I say? So you get a sense for the logic here. I'll give you
Some
a clue.
function, like
Okay,
some function of like differences, or
good. Why differences?
because you're talking about some transformation, that means you're like moving from point A to point B and you're transforming it under a particular symmetry or something like that, and then you want some kind of you want to see how everything changes under that particular transformation. So maybe
Well,
that.
yeah. So which one do you think? Like of the transformations, symmetry transformations we have, well, which one gives us the difference as a consequence?
The boosts.
Even simpler. Translations.
Yeah.
It would just be translations, because what I can do is I can translate my coordinate system to sit at the origin, to put this at the origin, right? And then I have
Yeah.
x2. So when you have 2 points in RD,
Mm-hmm.
and you have translation invariance, you can always translate
Right.
up
Yeah.
here, and then you
Basically,
see this is very bad drawing. So go on, Pradyot.
yeah, basically, is it something like you just like observe the particle moving or something like that, and then you're like trying to keep your frame along with the
Yeah,
particle or something like that.
roughly
Yeah,
speaking, yeah, no, that's for sure.
yeah,
No, the particle doesn't really have to move. It doesn't have to do anything in this context, but still,
yeah.
you can have this. It's just a change of your reference frame, and then you can sit on top of one, and then all you're really doing is measuring. Well, you're measuring the distance from the origin of this x2 here,
Mm.
right?
Yeah.
So in this new reference frame, it's a similar exercise to the one we did before,
Right.
saying that I just have a function of
Mm-hmm.
this. But we haven't exhausted our symmetries, right? Because we had RD, which was taken semi-direct product with SOD, right? So the rotations. So what do you think the implications of this part are?
Hmm.
It's so it means you have d degrees of freedom for your rotation.
Right.
No, but
So you have d z axis or whatever.
Well, but we have a symmetry here. So what? Just like how
Mm-hmm.
just like how the translation invariance meant that I don't really care where I put the, where I put the origin of this.
you
I
have
can always move.
again.
Hmm?
You have
Could you say that again?
conformal symmetry coming in because of that, or
Not yet, not yet. I mean, we're still in Poincaré, so we're yet to get to conformal. So
Mm-hmm.
we could move this here, right? And then we can say that x2, so x1 minus x2 is just all the function could depend on. But now, if you have rotational symmetry, okay, so let's think about the implications of rotational symmetry. So let me pull this vector out, right? This is a vectorial quantity. What happens to it under rotations? It'll rotate. Okay,
Where are you exactly pulling it out?
I'm just drawing it separately.
yeah.
Okay.
Yeah, just so that we can visualize what happens to vectors. So essentially, you have this vector which is x1 minus x2. I don't know if the conventions are the way people like or not, but so you have this thing, and under rotations, clearly it's not invariant.
Right.
I mean, that's what it means to be a vector, right? So whenever someone says that something's a vector, then you can ask under what? Like, let's go back to this notation I had for the Higgs field. I've written an index here.
Mm-hmm.
But we know the Higgs is a scalar. In fact, it's a pair of scalars. But they're scalars with respect to the spatial Lorentz group, or rotation group, since we're in Euclidean signature. with respect to the internal SU2 symmetry of the standard model, it's a vector, so-called doublet representation.
Right.
Right. So if I have, whenever I write multi-component fields, right? So if I look at the web and I have phi1 and I have phi2, right? Then under a rotation of space, right? So let's just say under a Lorentz transformation, well, these are scalars, so nothing happens to them. But under the SU2 of the standard model, then I have some unitary
Matrix.
2x2 matrix with unit determinant acting on phi1 and phi2.
Yeah.
So you see, as far as SU2 internal is concerned, this is a vector, right? So you can write this as 2. That's the way some physicists denote these representations by their dimensions. But anyway, so anyway,
it just opens up. It just opens up a sort of degree of degree of, like an extra degree of freedom or something like that.
Yeah.
And,
No, I was just illustrating the point that what a vector is, like what a vector is, sort of defined by how it transforms.
Sure.
Right?
Sure.
So now we can ask the same of our little x1 minus x2 vector here. Clearly, it's not invariant. And what is invariant? Like scalars are invariant, right? That's why they're scalar.
Yeah.
Like, if I have something that's a number, then I don't care if I rotate space. Like, what does it have to do with anything?
Right.
So how would I form a scalar out of this guy?
You'd probably
talk about the
just
distance. Just talk about the distance.
Yeah, exactly.
Like
the
displacement or whatever.
Precisely.
Modulus,
No, for sure. So in
have a
notation that we might use later, we could call this a vector with an index mu, and then I just use my metric, flat space metric, and then I contract it with x1 minus x2 nu, and I form a distance. Maybe I take a square root, maybe I don't, it doesn't matter. Like that just changes the definition of this function.
Right.
And that's all, right? Because if I wanted to determine this function, once again, I'd have to use some other features of the quantum field theory. So if you give me Lorentz invariance, this is all I can say. I mean, Lorentz invariance plus Poincare invariance is all I could say, right? So the question of having boosts versus just rotations doesn't change much because it just changes the signature of this metric.
Yeah, that takes care.
Right. So exactly. So let me just summarize in terms of this. Sometimes notation lets you see a lot. So mu is my space-time index. And if I was just talking about Euclidean signature, then this transforms this way. Right? But I know that x mu, which is contracted with now the Euclidean metric, stays invariant. Right? Nothing happens to it under rotations.
Right.
Because of the property, I mean, this is how rotations are defined, right? So
yeah.
So the reason why you might see this little riddle of indices, that someone might throw at you is to make sure that this happens, right? It's that lengths are preserved. Now, if you want to go to Lorentzian signature, all you do is you replace the rotation matrices by Lorentz transformations.
Right.
So if I take mu comma nu to be all the indices that are spatial, then they're just the same, right? And then I get boosts if I take either one of them to be 0.
Yeah.
These are antisymmetric matrices, so I only have these mixed components, right?
Right.
Maybe I misspoke. I'll continue before I come back and think about the implications of that. So you see the Minkowski metric has the same property that the Euclidean metric does, except with Lorentz transformations, right? So that's the That's the key notion here. Great. So let's go back to our game of having conformal symmetry, right? So now we have to add on to this to get to conformal invariance. Now, in group theoretic terms, it's written, okay, so in Euclidean signature, it would really be SOD, comma 1. Sorry, I'm not doing this right. No, I am doing this right. Right, so it's like a Lorentz group of a one higher dimensional space. Or in Lorentzian signature, this would be, so A minus 1, comma 2. So you have a one higher dimensional space of it's two time-like directions, and it's like the simple Lorentz group of that. But as far as our games are concerned, you really are appending to your Lorentz invariance while invariance. It's another way of talking about it, where I'm also considering what happens under this transformation. Right. So, there's a way of playing this game where you say, okay, so I'm skipping ahead a little bit because the regime where omega is constant and not a function of x is the regime of what are called scale invariant field theories. So scale and conformal invariance are not really the same thing.
Right.
So conformal symmetry is a little bit more, but let's just go straight for conformal invariance. I mean, it's your choice. Would you like to work it out starting from scale invariance and then moving towards conformal invariance?
I think we can jump to conformal invariance and then probably what happen with scale invariance.
Right.
Yeah, reflect. Yeah.
That would work. So now let's see if I can remember how this works. So what you want to say, you want to give a statement of invariance, right? You want to say that under Weil transformations, so I really want to say that this equals, so I define this on eta, and I want to say that this equals 2 delta 1 x1. I could be off by minuses here. That might have catastrophic consequences, but we'll wait and see. On x1, okay, 2 of x2 on my rescaled metric. Okay. Well, I should manage space better. Do this. So you have this relation, but you already know this fact, right? So the Poincare invariance is a subset of whatever you have in conformal invariance. So you know already it's a function of the distance. And what this condition lets you do is actually determine what kind of function.
Right.
So it's one of those exercises you do lots of times, but can never remember how it ends up going. But well, usually you would say, okay, if I took a constant, so if I just had scale invariance, right? What would this be? This kind of question. So basically, you think of the difference between these metrics alternatively as a difference between how I'm coordinatizing the x's.
Right.
So x transforms to lambda x, where lambda is just a constant version of this omega.
Yeah.
And then I'd have lambda raised to some power on the right-hand side times this other difference. So you're essentially talking about a homogeneity property. Right?
Yeah.
And so if I just had this homogeneity property, then that means that I have a function of x to the 1 minus x to the 2, the distance, which is homogeneous to degree minus 2 delta 1, yeah, minus 2 delta 2.
So just you're grouping together all omegas in the lambda matrix, right?
Yeah, essentially, I'm just rewriting the condition in terms of the x instead of like this metric.
Got it. You're
right?
absorbing that, you're absorbing the scale invariance into the, got it.
Now, so you can tell that this must mean, if I've got the signs here correct, that I want a function that looks like this, right? Homogeneity of a polynomial, so 2 delta 1 plus 2 delta 2. Right, so that's my G.
Yeah.
This was scale invariance.
Right.
Okay, so now for conformal invariance, you have to go a little bit further. So now you have to actually use omega that can depend on x. Okay, and in particular, you can take this to be an exercise. But if you take omega as an inversion, turns out to be a move you are allowed. So I take modulus of x inverse. Right, so under an inversion, what happens is that my x's go to x over the length of x. Right, so this is mu again. So if I take this function and then I plug it back in, you'll find, so I plug it back into this condition essentially. I plug it back into this condition. You'll find that something very mild happens. Okay, so to be perfectly honest, we don't know that the numerator there should be 1, right? It could be some constant. So you can call that constant so some normalization. You can call it curly n. So then if we add on our additional requirement, we will get curly n over x1 minus x2 to the power 2 delta. So basically, delta equals, oh, that doesn't look like a delta. Delta equals delta 1, which equals delta 2.
Right.
And otherwise, it's 0.
Right.
So otherwise, it won't satisfy this condition above. With omega equals 1 over modulus of x.
Yeah.
Right.
So you basically find that with just a symmetry, you have reduced the problem of computing this 2-point function to just the problem of finding these numbers. This normalization constant is inessential. You can always just choose. You can always just choose to divide all of your 2-point functions by this guy. Right? So it's not a part of the information that you need. This is what's important with this delta. Right? So all you've done is, so you've essentially used symmetry to determine the form of the function, not just that there is some function.
Right.
Right? Before you could say, well, we just know that we have some function, and then if you're lucky, you can use some identity to determine that function, some other quantum field theoretic identity. But here you can just look at it, sort of write the answer down. So this is why conformal emergence is very powerful, so that you can do things like this. And then you can now, you can also ask about the 1-point functions. So you could ask what happens to these.
0.
Good. Yeah, they're 0. So you can go about it the same way. You can start by just looking at scale invariance, and then you can say, well, at best they're constant, and at worst they're 0. Right? Once you look at conformal symmetry, you say, oh no, it can't be anything. So great. You have 1, 2, and then here's where you'd have to dig into textbooks, but it's the same kind of exercise, just takes a lot more time if you wanted to do it. But you can also fix 3-point functions up to so up to this piece of information. So these are constants. People call them structure constants.
Right.
Then your arduous task of playing with those other relations will tell you
permutation combination of the differences.
Exactly. So you have these differences, and I'll write these down as delta. So basically, you got delta 1 plus delta 2 minus delta 3. And then you have x 2, 3 of delta 2 plus delta 3 minus delta 1. And as you can imagine, the last term is x3, 1 to 1 plus 3 minus 2. Again, it's just conformal symmetry that lets you fix this. And so you've gone from determining infinity of functions to determining these structure constants. And if we had the time to get into it, maybe we could do this in the future, you'll find that the 4-point function can be fixed up to a function. What do I mean by that? So I'll take...
So you're referring to the OPs and...
Yeah, that's what we can opt to skip over today and come back to some other day, but...
Or probably like we can try to solve it on our own and like just post it on the group just to see.
Yeah. So we could write a note, in fact, where we detail how all this works, or even just find references where people do this. So here, again, you can play this scaling game, and you'll find that there's 1 minus 2 to delta something. Like, I'm just going to write it down schematically because there's a lot of choices that go into which functions to write down here, but the essential point...
you have 2 terms,
Delta 3, delta 4 is that you get this function, this conformal blocks, which depend on u, which equals x1, 2. This is the difference x1 minus x2 over x2, 3, and then v, which equals x1, 3 over x2, 4. There's standard definitions of these, and I'm not sure if I got these right, but they're called these cross ratios. You can prove that these are actually invariant under conformal transformations. And as you can imagine, I could form the other ratios. I could take v and u instead. Right? And then that would change the prefactors. I would change these prefactors. So that's why I said it doesn't matter too much. But the fact that you could have one or the other and they still represent the same quantity becomes a really powerful fact. In fact, it lets you determine all of these. And further fact is that 4-point functions are, if I calculate all the 4-point functions, you can calculate 5, 6, endpoint functions. And the reason for all of this is something called the operator product expansion.
Right.
Which is what we said we'll lay off of for now. So this is, this is all great. We'll have, we'll have a lot of fun one fine day when we catch up with the Bootstrap people. Okay, I keep saying Bootstrap, but we should say what that means. So you see that with this amount of symmetry, you can use just the axioms of what the quantum field theory is to determine all of the quantities you want to compute.
Right.
Correlation functions.
Yeah.
You don't need to write down any Lagrangian, don't need to do any perturbation theory, you don't need to do any of that. So you just have what's called the conformal data, which is a table of these deltas, right? These deltas, and then you have these 3-point functions, you determine them, and that's it. That's everything. That's the theory.
Right.
So the Bootstrap program is this research program that aims to solve, in quotes, conformal field theories by doing this. And how they do it is that they essentially use semi-linear programming on the space of these deltas and C's.
Right.
So they find inequalities, right? They find theories that can't be because they don't satisfy. So you find infinite theories that can't be conformal field theories, and you start to exclude them. So I have some space and I start to like draw these lines which tell me that there are inequalities. And what you can find eventually, so their most celebrated triumph is on the space of, so let's call this epsilon, sigma. So these are two operators that feature in the Ising model in 3 dimensions. You can say, well, I just look in this space. I have all my consistency conditions. What kind of field theories can I find? Okay. And you find that, well, okay, I have some big inequalities. I start to carve out some space. And then I keep running my program. I keep looking at higher and higher point correlation functions. So this kind of region starts to shrink, right? So I work harder and harder. No, this is not me. This is people like David Simon stuff, like serious people. Oh, sorry. This is epsilon.
Right.
This is sigma. And you can actually shrink this region down to a tiny island.
Right.
Right. This is also an exaggeration of what they actually find. In fact, the island they find is so tiny. So this is the 3-dimensional Ising model that they're studying. Basically, it's a theory that conformal field theory that has the internal Z2 symmetry of the 3-dimensional Ising model. But their island is so small that it falls under the resolution of what numerical calculations can do. So you can use Monte Carlo, lattice methods, Monte Carlo methods to determine these quantities, but you have an error bar.
Right.
The numerical error bar is larger than this island that these people found using only consistency, right? And the point is that means that this little thing is actually closest to the experimentally observed values of these quantities for the 3-dimensional Ising model.
Wow.
Right, so it's a really, really fascinating program. They're doing very, very inspiring things. I mean, this is one example. Another example is that there's a web of connections and dualities that relate M theory and whatever. You can compactify M theory and obtain a certain kind of conformal field theory in 6 dimensions, so on. But you take those supersymmetric conformal field theories to Bootstrap, and you can actually compute corrections to the 11-dimensional supergravity action. So you can compute all these higher order corrections, which there's just no framework otherwise to be able to do this, but you can get those from doing the Bootstrap. So this is work by people like Silvio Pufu and collaborators. So Bootstrap is very powerful, but we'll go back to something simple for now. So we'll talk about simpler conformal field theories, for which we have other methods to compute things. So your favorite method is maybe perturbation theory.
Yeah.
So all of your quantum theory textbooks will teach you how to do that.
Yeah.
And so we'll look at free massless scalars. Right, so this is textbook stuff. You have an action, d dimensions.
Yeah.
And then you have equations of motion. That come from varying this action. And the point is that the action is a number, right?
Mm-hmm.
It's an integral of some function, it's a number, which means that it has no dimensions.
Right.
Right? So you can count the dimensions of length we have here. So we have dimension d coming from this. We have dimension -2 coming from this.
Yeah.
Right? So 2 times whatever dimension will endow phi plus t minus 2 is 0.
Yeah.
Right?
Mm-hmm.
So we're basically able to determine Yeah?
Yeah.
You agree? So,
Yes.
if you take 4 dimensions, it'll be like length dimension -1, and or mass dimension +1, right? So this is minus of what people normally call the mass dimension, since we were counting lengths here.
Mm-hmm.
So whatever, so delta is like whatever extra thing that you want to give the particle, characteristic that you want to give the particle, you stuff that in the delta, something like that.
Well, I mean, it's really just like dimension analysis we're doing here.
Yeah.
Right.
Exactly.
So I should explain. If we're in units where C equals 1 equals h bar equals g Newton, so you can always find these units. They never tell you in school. You mostly waste your time plugging these into expressions. But what this does is it basically takes length dimensions, right, and relates them to mass dimensions.
Okay. Yeah.
And so this quantity, which has dimension d in length, would have dimension -d in mass, or energy, whatever you. So energy and mass dimensions are identified.
Yeah.
Length and time dimensions are identified, right? So keeping true to relativity. And then you'd have, sorry, there's some chaos here. So you'd have length dimension d, mass dimension -d. And that's the kind of counting I'm doing. So I just want to know, what are the dimensions of this field phi?
Yeah.
And you find that you get this quantity. And so you see a few things here, especially if you go down to dimension 2, then this is dimensionless. So phi is dimensionless. It's a pure number.
Okay.
We'll just proceed. So, you do open up any of your favorite quantum field theory books. They'll start by putting this in an action and working out the simple Feynman diagrams in this theory, and then tell you what the propagator is, Wick's theorem, et cetera, et cetera. So, if you were to draw Feynman diagrams for this theory, all it really has are flyby interactions.
Right.
So you see things like this. There are no vertices. So you can have this, you can have loops if you want. Well, actually you can't.
Basically, it's basically Newton with which law is it first? Inertia, law of inertia, something like that.
Well, I mean, it's just, they're just non-interacting particles.
Yeah.
So they just fly around. That's all they really do.
Yeah.
So this is with 2, and then for higher, you have more particles. That's all. So they don't interact.
Yeah.
Right. The only loop you can have is the closed loop.
Yeah.
A particle just goes into itself. I don't really have a vertex to adorn whatever sits over here. I can't really connect this to anything.
Yeah.
Right.
Yeah.
So I'm just, I'm in a very simple setting. I have this very simple theory, but I draw all these diagrams. What do they mean in like symbolically? Well, this is just a way to rewrite. So I have 1, 2, 3, 4. Then this term is the propagator between particle 1, particle 4 times the propagator between particle 2, particle 3,
right.
plus 1, 3, and 2, 4, and so on.
Yeah.
Permutation combination. Yeah.
Exactly. So that's exactly the point. You give me n points, and I'm just going to permute. So I'm going to choose 2, and then I'm just going to keep connecting them with propagators.
Right.
Right. This is called Wick's theorem.
Right.
Right. So there are no odd point functions, and all the even point functions can be reduced to so-called 2-point functions or propagators.
Right.
Right. So what? Let's just write down what that means. Okay. So this one, as you can imagine, is gx comma x. This is 0.
Yeah.
You go back to yourself. But what Pradyot was talking about was, you give me some number of points, right? First I count, are they odd? Well, there's no process to go from here to here, right? Say they're even. Then my task is to suit together these points with propagators, right? So this is free field theory. Let's make that clear. Yeah. When you have interactions, then you can have points in the middle, so to speak, where these particles come into each other, and so on.
Yeah.
But here, there's just an exercise in permuting. So I can go there, and then this one can go there. So then I can go here, and then I can go take this one there, and so on. So I could just connect these points in how many ever ways I like.
Right.
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 It's called Wick's theorem. But what do I need to know? I need to know this g. I think that's all I need to compute. Right. The 2-point function g.
Yeah.
Once I know that, I know everything about this theory. Right. So turns out it's not that hard to compute, and we'll chalk this up to another exercise. But you find that for any 2 points, x1 and x2, for the free massless scalar, I get 1 over the distance between their separation to the power 2. Oh, this looks familiar. Okay, so before I go and talk about how this is similar to, why this is a CFT and so on, like, just go over how you get this. Don't have to do the calculation, but like
basically, yeah.
Yeah, so I'll write, and then you guys can go on to explain what to do.
So, yeah, you're basically trying to form a scalar of this and the propagation, and how you do that is basically the translation.
Oh yeah, no. I mean, we're good with that. So that's the guessing game. I was just saying, like, if I was looking at a quantum field theory textbook, then people would write down expressions like this, right?
Yeah.
Yeah. So you would start with.
Yeah. It's like it's basically a particle propagating, and if the field changes from phi1 to phi2, then you have some sort of action related to that, and we are just calculating or computing the action.
Yeah.
So we'll just unpack those words. So how you do this, right, is there's usually some tricks, and the neatest trick is this one. Okay, so I'll go through the steps. So it's not call it a limit. I'll write this. So 1 over z is just a normalization. So
right.
Z is actually my 0-point function. It is
Okay.
okay.
Yeah.
That's all it is, and I'm just computing expectation value, and this is how Feynman teaches us in the path integral formalism to do that.
Yeah.
Right. So the trick that is very commonly used, and we shall also use, is this one. X, y1, x1, x2, at j equals 0.
Yeah.
Okay, so I've introduced what they call a source. Why is that useful or relevant? And the answer is because you can take derivatives.
Okay. Yeah.
X1.
Yeah.
J at x2.
So there's some. Yeah.
Oh, I forgot the measure here. So I'll write it like this, but what this notation means is that I have a functional measure.
Yeah.
So basically you're taking the flow out of the integral. You're not talking about the flow anymore, right? I mean,
You mean going from the source to the sink? That's what you mean by flow?
I think that's what.
Yeah.
Right. Yeah. So, well, exactly. I'm taking it out of the integral. And why would I want to do that? Could ask. And the reason is because this is a Gaussian integral, actually.
Right.
It's a Gaussian integral in this
Right.
phi. Okay, and let me just go through the formal steps, and then you can convince yourself that. Okay, let me just go through with this so that we can all see why it was useful to invert this Laplace operator delta. So one fine day we'll invert it. But when I do this, okay, when I write this curly d phi, I've basically normalized. Okay, so another way to put it is when I write curly d phi, I define that measure so that the exponential of phi, I shouldn't write comma, but basically integral phi squared is 1. So there's going to be some 2 pi's and all these other things. I just absorb it into my definition of the measure. That's what I mean by this curly d phi.
Right.
Okay, so I'm not going to write down 2 pi's and all this square roots of 2 pi's and the things you'd usually see in the.
Yeah.
Right, but instead, what I'm going to get is no integral, but this expression. Write this in quotes because that's a nonsensical looking expression.
Yeah.
Right? But I mean, okay. So just to clarify, if I were to do this with matrices, right? If I were to do a matrix integral, then what I'm using is this property of Gaussian integrals with matrices. So if I have A, where should I put this? Why am I calling? Okay, so if I have A dot M dot A, the one here was useless notation, then the result is going to be square root of 2 pi times some other stuff to some power, everything that I'm not including. So I can just put that in the denominator of dA. Okay, doesn't matter. But okay, sorry. There's the B dot A here.
Yeah.
Then I get minus B dot M inverse dot B.
Yeah.
Over the determinant of M. Right, so that means that there's also going to be the determinant of this operator here.
Yeah.
But I don't care about it too much.
Yeah.
But actually, would they even be the determinant? Not yet. Let's actually look this up on Wikipedia. So
Jump to there should be a jump to,
yeah, so this is all simple. Okay.
yeah.
They're not looking at the use case that we care about, though. I suspect there wouldn't be. No, there would be the determinant. Yeah. So basically, this comes from completing the squares. You see, like this B M inverse B comes from completing the square, and then once you completed the square, what you do is you shift the integration measure for A, and then when you shift it, you do the Gaussian integral as normal, and you get the result from the Gaussian integral, which is this 1 over determinant to the square root. Right, so it's like square root of 2 pi to some power over the determinant.
Yeah.
But now the square root of 2 pi, I leave it away. It's constant, and the determinant of m sits here, so the determinant of phi sits here. As far as our exercise is concerned, this doesn't really count for much because 1 over z would have this determinant in the numerator, and it ends up canceling, and I'm only taking derivatives of this guy.
Right.
So this determinant would come when I ask for g x comma x. So I'm going in the circle.
Right.
Okay.
Makes sense.
So the crucial point here is that these derivatives only hit the exponential. And what does it give me? Well, it gives me, sorry, I take the limit j equals 0 in the end, because j was a fiction that I invented for my calculation. And it gives me, in quotes, 1 over delta of x1 comma x2. Okay, so what does this expression mean? I mean, obviously, dividing by differential operator doesn't make any sense.
Yeah.
But let me just rewrite this as g. The closest thing that can make sense is the so-called Green's function.
Right.
That's what this inverse means. Because the delta function is the functional generalization of 1, if you like. Okay, so if I multiply this with its inverse, I want to get 1. That's the sort of analogy that we're making here. So that's what we're after. We're after this Green's function now. Right? And you could say, well, how is that more than an analogy? Well, you need to start integrating to see why. Right? So in the very abstract notation, I want delta dot g to equal 1, right? Literally. But what does this dot operation entail when I'm talking about functions? Well, it entails integration. Right? So I want to do the integral d dx1. It doesn't matter if it's 1 or 2. Right? And then I want to take fx1, g of x1, x2, and I want this to be 1, the number 1. And that's why the delta function would come in. This is like the unintegrated version of this equation. Great. So now we have, without really lying to ourselves, convinced us, gotten to the point where we say that, oh, this is something worth determining. I haven't explained why for the free massless scalar case, it just equals this 1 over, why it just equals this function 1 over x1 minus x2 whole squared.
Right.
But if you really wanted, you could say, okay, I do a Fourier transform, maybe an inverse Fourier transform. Okay, to the power d. And then I can, so the nice thing about Fourier transform is that delta is no longer a differential operator.
Yeah.
It becomes multiplication by p.
Yeah.
Okay, so I have what? 1 over p squared, right? And then this doesn't really make sense. You have to add this I epsilon. and then make sure that you play with all the contours correctly. And you have e to the I p dot x minus maybe. And then play with all the contours correctly, and then convince yourself that you get this function.
Yeah.
Up to some of the normalizations. But this is how you would do the exercise. This is how you would actually do the exercise.
Mm-hmm. Yeah.
If you wanted to get this. So there's a way, and you can look that up. But we get to see why this is crucial for our current exercise. And we've also seen why this non-interacting theory is conformal. Well, have we? No, I don't think we have, but let's just go back and say that the fact that I'm considering this, well, the fact that this is dimensionless, I mean, there's no scale in the problem.
Yeah.
It's dimensionless, it's Lorentz invariant. You can check the other axioms, they're all satisfied. But more importantly, the fact that the two-point function takes the right form is what's crucial.
Yeah.
So you have the two-point function taking this form, which is basically what we had with the two-point function of conformal primaries, except we had delta now equals 1.
Yeah.
Delta supply.
Yeah.
Great. So how to connect that delta to our dimension delta is another exercise I encourage you to do. So there's a difference. So you have to take the difference with the dimension d at some point. And anyway, there's a way to translate these things.
Mm-hmm.
But let's continue with our exercise of, or let's continue and see a puzzle. So remember when we went to dimension 2, in dimension 2, this was dimensionless, right?
Yeah.
Because we had d minus 2 over 2. Okay, that's neat, but let's ask, how do I invert this guy? So now I'm interested in finding my Green's function. Right, so we could say do Fourier transform, notice difficult things. Well, okay, that's worth seeing because you get a feel for what could happen. So you basically have d2p over p squared, some e bar I px. So you kind of get the feel that this could end up looking logarithmic.
Yeah.
But let's, I mean, this is just vague intuition. It's not.
Yeah.
I mean, doing the whole thing would require us to look at a contour integral. We might as well just go to complex coordinates.
Yeah.
And then play with contours there. So I introduce my friends z and z bar. So then we can ask, what is this? Okay. Whoa, there was a connection error. So just a second.
Mm-hmm. I'll just pause the recording, I guess.
Sure. Nice. Back. Okay, so little exercise. What is this going to become in complex coordinates, guys?
This is basically the distance, is it?
It's
Oh, no.
zero.
So this is like my nabla x1. So this is my notation for the Laplacian.
Ah, I see.
So dx1 squared plus oh, it went away.
You just like okay.
Okay, that's notation for it.
Mm-hmm. Okay.
So by complex coordinates, I mean in terms of these guys.
So z bar, dou z bar.
Yeah, exactly. So just what Rahul said, it's going to be c d c bar. Yeah, let's write it as d bar c bar. It might be redundant, but it's nice.
Mm-hmm.
So what do I mean by
Okay.
that? Well, just remember that if I have a plus ib times a minus ib is equal to a squared plus b squared,
Yeah.
right?
Okay.
And then
Uh,
here we'll take a to be d sub c and b to be d bar sub c bar.
Yeah.
Oh, sorry, wrong. So what I want to do, I want to take a to be d sub x and b to be d sub
yes.
x1, x2. So if I take this to be x1, I take this to be x2, and then I get this relationship. Because dx1 minus I dx2 is d sub z, and then vice versa for z bar. That's great. So we'll keep pushing on. Continue. Now, another seemingly tangential fact, which is Cauchy's theorem. Closed contour. Right. So basically visualize on the complex plane of Z. I have my W, where W is a pole.
Right.
And then I have some contour wrapping this pole.
Right.
Cauchy's theorem tells me that this is my result.
Right.
And doesn't this look an awful lot like what you want the delta function to do?
Mm-hmm.
Right? Okay, sorry. There's a 1 over 2 pi I maybe.
Yeah.
Tell me that.
We've been ignoring all that all this
Yeah,
while, so
yeah,
it doesn't matter.
Ignoring. Yeah.
yeah. So essentially what's happened is that this function has taken over the role of the delta function in Z.
Mm-hmm. Right.
And we're after the delta function x1, x2, which is really this product of delta functions.
Right.
So we have a series of many products. We have a product of differential operators, right?
Mm-hmm.
And we have a product of delta functions. And what do we want? We want this to equal the action of dz and dz bar on my Green's function.
Mm.
So, well, if we look for a product here, what could it be? The log.
No.
Right?
Yeah.
Do we agree?
Yeah.
Maybe there's pi's, maybe there's stuff, some number. Right, so it's 1 over 2 pi I, 1 over minus 1 over 4 pi actually. We could actually write down that number.
Yeah.
Oh, it's embarrassing. So I'd have a 4 pi squared maybe, and then yeah, so I'd have 4 pi squared. Right, so we're good.
Yeah.
We've got the logs as the Green's functions, but here's a surprise. If we take this has to equal
Hmm.
Oh no. So turns out that this is not a good conformal primary operator. It's
Hmm.
not satisfying the property we want.
Right.
And it's, again, I mean, if we went down to Fourier transforms, it's because the denominator is always p squared, but the numerator before would always compete, it would be like higher power,
Right.
right?
Mhm.
Here, the denominator and numerator are just, it's more like a Mellin transform of the exponential in a way.
Mm-hmm.
It's like a dp over p type transform, which is no good. So then we can ask, okay, which function? So what can I form so what can I form to regain my conformal field theory 2-point function? This doesn't mean that this is not a conformal field theory. Obviously, there are no masses, there's no scales. Like what could happen here, right? So I want a new O1. Before, in free scalar field theory, I could take my O1 and O2 to just be the field phi itself, and then I would be fine.
Right.
We know that O1 and O2 have to be the same operator. So let me not write these differently. So what can we have here?
Hmm.
So I have phi, but yeah.
Yeah. The exponentiation.
Yeah, that's good. So we can write down exponential functions.
Yeah.
Right. So I could write down the one is unnecessary. That's just a phi. X2, there's an X2 there. Right?
Right.
But we could also write down derivatives, right? Because I can take derivatives with this.
Yeah.
Yeah.
Right? So it could be Z
Z bar.
or Z bar, essentially. Yeah, you're right.
Yeah. Okay.
And both of these will give me this kind of scaling that I want. They're different kinds of operators, but you see now how two pieces of string perturbation theory you can already see. They're already visible.
Right.
So if I was talking about string theory, then I wouldn't have just, so instead of having phi, I would have many phis, right? So let's call it x a, right? So this number runs up to like 26.
Yeah.
Okay. And
We have
then
like a whole.
what would I need? I would need a vector of these k's, right?
Yeah.
And this is what they call a vertex operator.
Yeah.
But then if I took the derivatives, I would obtain a current.
Current. Yeah.
So then this is what's interesting. You find that the property that vk prime of x and y. So for this to be non-zero, right? If this is of the form of 1 over x minus y to the power of 2 delta, this can happen only if ka equals some m squared.
Yeah.
In other words, these act like momenta in this target space, of this target space. And the requirement that you get, so essentially the spectrum of the theory, right, the spectrum of these 2-point functions gives me the string spectrum in the target space
Target
of
space.
the excitations.
Okay. Makes sense.
right? So all these different m's are just different v's, right? It's like
Yeah.
they
Yeah.
have different k's, but then they're all just different v's.
Yeah.
So the simplest one would be the tachyon, and then you go from there. You get the graviton, you get everything else, all the higher massive modes.
Right.
And if you're careful, if you really pay attention to how the delta comes about in this exercise, I mean, you do the exercise to determine delta for an exponentiated function, you'll find why the graviton has to be massless and so on. So you get all kinds of nice things from doing that. But yeah, this is like a very neat piece of CFT technology in 2D, where, I mean, a lot of things are different in 2D, but yeah, it's this very interesting property of having a logarithmic two-point function of the fundamental fields. Right. So one aspect is this, but you could say, well, do I have to do string perturbation theory to know? Well, sorry, to know what happens here? The answer is no. In fact, think of situation where I just have phi, and then I want it to be periodic. I want it to be a compact boson. Wow, these are vortices. So in the XY model, also this is the right conformal primary to be studying if I'm near the Costa-Stalis transition. Right. So there, there you actually have a family. How you normalize this K, it gives you an entire family of conformal field theories. It's the radius of the compact direction. Yeah. And similarly, you can look at these currents, and then it's simple to work out what their two-point function is or what their delta is. I mean, their delta is just one. Yeah, that's related to some properties of theirs. But I mean, here's another fun fact you can very quickly work out. You can work out what the stress tensor is from just these currents. Yes. Yeah. Right? I was thinking about that. Yeah. Yeah, because the stress tensor is always of this form, right? D phi, d bar phi. Yeah. Well, sorry. Well, this is d phi, d phi. Then t bar is d bar phi, d bar phi. Yeah. And so on. And then the stress tensors OP gives you the central charge. We didn't go into OPEs, but that's a way to compute the central charge. And the fact that you can express the stress tensor as a product of currents is something known as a Sugawara construction. It's an example of what's called a Sugawara construction. And when you have additional symmetries, so if you have these scalars all transforming under some Lie group, then the OPE algebra gives you what's called the Kac-Moody algebra. The OPE algebra of these currents gives you the Kac-Moody algebra. So anyway, that's part of what makes conformal field theory so vast and interesting. This is a very deep subject. And you see, just here we've gone from like Ising model to strings to vortices and so on. And yeah, so let's stop. But it all started with just talking about these symmetries. They're back here, right? So our exercise was just to like understand how to do this better. Yeah. And that's just a big theme in theoretical physics and mathematical physics. Yeah. Try to use symmetry to, as far as you can, to see how many implications fall out of that. Yeah. And you see with conformal field theory, it's so much so that most of what you think are details about the theory don't matter, right? Yeah. All you need are these deltas, right? And these C's. Yeah. Now, even in 2 dimensions, that's true. In fact, there's something called Liouville theory that was famous for having been solved completely through this method by Georg Teschner. And there, of course, it's much more complicated because these aren't like just, like these aren't discrete. You have like continuum of these. And there's some very inspiring work. You have something called the DOZZ formula to obtain all these 3-point functions in Liouville theory. But yeah, you can solve that theory completely. Like you would to the Teschner. yeah, so anyway, the point is that this data is what defines the theory. It's not if there's bosons or fermions, or if there's some action, if there's some term in the Lagrangian.
Right.
You can determine all of that later on. You see, when you talk about, so let's take the Ising model in 2 dimensions. You find that there, actually, it's a theory of free fermions, right? Ising model in 3 dimensions, I don't really know. It's fermions, they're not free, something happens. It's just kind of weird. In fact, there's ideas that even go, I mean, this goes back to Polyakov, but you say, okay, let's take, so you have a hypercubic lattice, right? So you have, I'm bad at drawing cubes, but let me try. So in my Ising model, I have some number of cubes inside some really big one, right?
Right.
So this pattern goes on. So I define it on a lattice. But what happens is that I have domain walls, right? So here I'll have spins up, so at low temperatures. Spins up here, spins down here, right? I have some other domain wall, and then I have spins up, and this keeps going, right? Spin down there because I have another wall coming in the middle. Polyakov had an idea, which was to say, think of these domain walls as the trajectory through space-time of some string. So I slice it up. So could these domain walls be a string world sheet? And the answer seems to be yes.
Oh, wow, okay.
So there's this very nice paper by Creevy and Nabil. That was very, very nice story where they actually show you how this ends up working. You can write down an actual string theory for the 3D Ising model. Now, the point of this is just to say whatever the picture is, right?
Right.
So let's see some nice picture in this. Yeah, so they work out the rules for the interactions of these strings, and so there's a lot of these complicated vertices. And at the end of the day, they're, like how exactly you end up working it out is just it's just a matter of like adding some irrelevant terms, right? So the universal information is still captured by whatever's going on in this little island here.
Right.
Right. So this information is still all you really need.
Yeah.
Right. And then the rest of your work is to see, okay, well, what's the picture that describes it best? Is it this thing? Is it the one in terms of something else or whatever? So this is just another example of the power of what's going on here with this whole Bootstrap program. And there's a historical context to this too. The first kind of Bootstrap people tried to study was S-matrix Bootstrap. You try to constrain the S-matrix completely.
Yeah.
Now in just like quantum field theory, and you don't care their fields, so nobody really thought about field theory much. Or like, okay, forget all that, just work everything. And they didn't get very far. It was as popular as string theory is today, back in the 60s. And then Glashow, Salam, and Weinberg came out with electroweak symmetry breaking, through field theory, and there were subsequent experimental predictions or experimental observations that confirmed that to be the right picture, and then that was it. It's like people were like, yeah, no, thank you, don't need S-matrix Bootstrap. So yeah, it's been a back and forth though, because you see now this comes back, and it's like better than where we can't really use our field theory knowledge very well, we can use these techniques. There's a new S-matrix Bootstrap that's come about.
Right. Yeah.
There's a resurgence in that, and string theory was actually born out of this S-matrix Bootstrap story.
Yeah.
Someone tried to give another kind of picture. Yeah, so it's an actually very interesting tension in theoretical physics about how you want to, like, what direction you need to go in order to be able to come up with better explanations. Do you want to be very agnostic to the picture,
Right.
and say that I'm only interested in the principles that let me compute these quantities? Or should I really be worried about whether I should be thinking about the Ising model in terms of this weakly coupled strings, or in terms of some other field theory, in terms of I4 theory that's critical, or in terms of some dualized something else? So, I mean, only time can tell, right?
Yeah.
It's one of those things like you don't know. See, if you just were concerned about the S matrices, you could never talk about a lot of interesting phenomena. You couldn't talk about things like spontaneous symmetry breaking very easily. I mean, you couldn't talk about it at all, right?
Yeah.
Because what is a potential, like, you're talking about the potential for a field, and you're talking about, like, you just can't, I mean, it's a very simple thing to do once you have it, but if you don't have that quantity, if you're not thinking about it a field, you don't know what that is.
Yeah.
Right? So, yeah, anyway, so this is just a little glimpse to stuff like that. Yeah.
That was good. Yeah.
It's fun.
A lot of stuff there. Yeah.
Yeah, no, I mean, we should write some supplementary material, or, like, at least compile some notes. But I mean, yeah, people should ask about which corner of this tree of notes that's essentially formed on this board now they want to know more about. And yeah,